I'm Knapp. I'll be talking about applications of convex optimization. Okay, so I'm going to be talking about, Nina's given most of the introductory material for what I intend to do. But I'm going to sort of introduce convex optimization in a slightly different light, particularly talking about applications. I mean, why do you want to do it in the first place? I mean, of course, it's fun, math, but sometimes there are other reasons for doing things, which I don't always see, but that's a lot of you might have that. But basically, way to think of convex optimization these days is it's really like an extension of linear programming. So linear programming came sort of to the forefront in the 50s and 60s, and it opened up because people could solve with the simplex method and then other methods could solve larger problems. Suddenly, applications for it just became enormous. Well, convex optimization is sort of in that stage now. And so the number of applications people are figuring out what to do because of the applicability of efficient solvers are just sort of blowing up. So that's kind of the theme for the presentation. I'm going to show a very tiny subset of examples, but hopefully that'll give you some of the flavor of the breadth of what you might possibly be able to do. Okay, so let's talk about optimization in general. I mean, optimization is sort of throughout science. We need to find things that are optimal or find the best solution or something like that. And typically, mathematical optimization, there's three different categorizations, whether a problem is linear or nonlinear. Okay? The next one is whether a problem is constrained or unconstrained. Okay? And the third one is whether your optimum you're finding is a local optimum, so is the landscape bumpy and I find a little pit here, or is this the best possible optimum out of all possibilities? Okay? So now, when we think about convex optimization, I'm going to recategorize things. So this is sort of a new paradigm shift. Instead of thinking linear and nonlinear, we now think of convex and general nonlinear problems. Because linear programming is actually just a subset of convex optimization. Okay? And we can think of constrained, unconstrained, and local global. But for convex optimization, the latter two categories are pretty much irrelevant because for any convex optimization problem, if your function is convex, you can transform it into a form like this, where your objective is linear. Okay? So any convex problem is actually a constrained problem, in effect. And if it's not constrained, it's going to be unbounded in solution. So there's kind of no point in doing it anyway. So that one. And the other big thing is that a local optimum is always a global optimum for a completely convex problem. So you don't have to worry about searching all the bumps and valleys. Convexity guarantees it. And again, Nina showed convexity. Think of, convexity is like if I have a set, I can connect 2 points without going through the edges of the set. That's convex. And a convex function is a function like x squared, and any 2 points in the graph, above the graph of the function, you can connect. So that's the essence. But we always typically transform convex functions as an objective into a linear function, and so we're always talking about convex sets. Okay, and here's a bit about why it's become mainstream. I've already mentioned that. It's the good solvers, okay? But they can reliably solve problems. So, I mean, typically if you see a linear programming problem, you go, oh, I know, I can solve that. I can call Cplex or blah, 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 and it's done, right? Well, the convex solvers are not quite there, but they're pretty darn close. So you get a convex problem, boom, you can solve it. You know it's a solved problem. Now, general nonlinear solvers, no way. Okay, maybe you'll get a solution, maybe you won't. Maybe you'll work for n minimize, wait for a week and see if it gets anywhere. But these are pretty certain things, and that's why it's such a big thing. There's some other key points, okay? I'm emphasizing this. The optimum is global, so you know you have the best solutions. Most problems are solved. Okay, conic problems have a dual problem, and I'll show an example in my examples of using the duality theory. It gives sensitivity and other things. And also, this I think is actually a really important one. Most nonlinear solvers require smoothness to get derivatives to be effective. Well, convexity, those cones Nina showed you, they weren't smooth. They had corners. Okay, and that's very typical in the convex. And the convex solvers don't care about those corners. Just like a linear programming thing, you have a polygon, the optimum is always at a corner. So you need those corners. Okay, so those are, I think, really important. So here are the applications, and I'm going to go through a lot of these fairly quickly. I hope I get to them all. But Shows them in finance, data fitting, signal processing, image processing, geometry, and graph theory. And that's only just a subset of the fields that convex optimization is being used for, okay? And I've chosen examples I hope will be illustrative of how you do modeling, but also the breadth of applications. Okay, so let's start with finance. Okay, I want to make some money. So we've sort of generated a really artificial possible portfolio of stocks. So, and the mean return on these stocks is like 20, which is not very realistic. But okay, we're playing math here, so it's okay. But the concept, and then we kind of covariance matrices. I'm just showing the diagonals of the covariance matrices to give you an idea of how risky, like this is a wicked risky stock. This one is pretty safe. Okay, so what we want to do is we want to balance the return. We want to get a good return, but balance that with the risk. Because of course you can get the best return by taking this one stock, which has the highest return. But that may have a bigger variance than you're willing to accept in terms of risk. So let's look for a balance. Okay, so what we're going to do is we're going to say, find a weight vector. So we're going to weight each of these 6 stocks with W1, W2, so on and so forth. And those have to add up to 1 to make our entire portfolio. And our return is going to be the means, that mu column, dotted with the W vector. So it's going to be the sum of the mean of the returns. And the risk is going to be determined by this covariance matrix, which I've just shown you the diagonals of. But it's actually a whole matrix. So this is actually a quadratic. This is a quadratic objective. And what we're trying to solve for is, what are the weights I need to do? Okay? Now we're going to set up a risk aversion parameter. I'm not, my financial advisor tells me I'm pretty risk tolerant. But other people I know are very risk averse. They don't want to take any risk. So there's always a, depending on the person you are, so this alpha sort of tunes that risk tolerance. And again, if we had real stock data and stuff, we'd be able to tune that more to the market, but that would be too complicated for this presentation. So again, we have weight constraints. We want the weights. We can't buy a negative amount of a given equity. So W has to be greater. Note this is this vector greater than or equal to 0. So each component has to be greater than 0. Plus the total has to be, our entire portfolio, the weights have to add up to 1. So those are our constraints. So all we have to do is, suppose I fit in with alpha equals 1, so my risk tolerance parameter is 1. I can do this, and I should have been entering these things as I went along. I was too busy blabbing, sorry about that. Okay, quadratic optimization, and
you need to evaluate the.
Oh, I forgot to do that. I forgot to do this. Thank you, Paratosh. Now hopefully this will work. There we go. Okay, so now I have weight. So basically this tells me that I want to pick the last 4 stocks, and I want to ignore those first 2. And if you take a quick look at the portfolio, sure enough, those are the ones with the lower returns, and they have comparable risks. Okay, or I could be more risk averse. Say my risk tolerance is pi. Then you get a different weighting of stocks, and you actually buy a little bit of those less return ones to balance the overall risk. Okay, now here's a plot. Quadratic optimization, as you notice, is quite fast. So I can actually solve hundreds of problems. Here I'm doing 1,663 different realizations of possible weight vectors. Okay, and I do that, and I can compare. So these are the random realizations down here. Okay, and this is my front found by convex optimization. So it always maximizes the return for a given amount of risk. So that's sort of a classic, and there's all sorts of finance problems you can do that get more sophisticated. And the real way to do it is to sort of estimate the covariance properly for the stocks. And Michael could probably help me with that. But again, we're keeping these. Okay, so another whole set of applications this is kind of one of my favorite ones because I always like approximating things and fitting things, is data fitting. Okay, so we're going to explore all sorts of different data fitting problems and how we can do it. So let's consider fitting a cubic polynomial for equally spaced points. Okay, So a cubic polynomial can be given by this basis, okay? I'm just taking a small set of points so you'll be able to see, not because the solvers can't handle it, but because I want to keep the problem simple so you can kind of see what's happening, okay? And the Mathematica has this beautiful function that's been there for version 1 called fit that just, boom. And this just uses linear algebra to find the fit, okay? But it actually is, that linear algebra is solving a minimization problem. It's finding the least squares deviations, okay? And I can show this plot, okay? And you'll notice that these points, so that's my fit. I chose the points perfectly so the fit wouldn't be that great, okay? Now, another way, I'm going to show you how the linear algebra works because that sort of leads us up to how to model the convex optimization problem. Okay, so we've got a matrix A. This is called the design matrix. Basically, I'm just taking the basis functions times -3 to the -3 to the -2, so on and so forth. That makes the so-called design matrix. And then the linear algebra problem is just least squares of A comma Y. Okay, and let's see. Yep. Okay, and that gives me exactly, if you look, that gives me exactly the same coefficients I got with fit. And that's actually how fit works. Fit makes this design matrix from your basis. It solves least squares. Boom, it's done. Okay, but can we do more? Well, with convex optimization, we can. So one thing that the least squares has is it's quite sensitive to outliers. So if you have a whole bunch of points which fit along a curve and a couple points which are way out there, those two external points tend to pull the curve away from the proper fit and do that because the penalty of square is quite strong as they get large. So another way to do it is to do what's called L1 fitting, okay? And that's actually just a linear optimization problem. Now, I could actually solve the L2 problem by using norm of plus with norm 2 norm. Now, why am I using this inactive of plus? Okay, this is one of the flies in the ointment of our modeling that we're still trying to figure out how to do. The reason is because y is a vector. So, and this is symbolic, so this would, our list of, if I just had plus, it would thread over that, and it would give something the wrong dimensionality. I want to have this not threaded until A dot C is kind of computed. So that's why I have that inactive plus. Okay, and you'll probably see a few of those. Okay, so I can plot the L2 fit and the L1 fit. And as you see, the L1 fit actually goes, it's sort of, in this case, it thinks these 2 points are the outliers. Okay, and it's quite close to the other points. Okay, well, that's a property of L1 fit. Well, we don't have to, with convex optimization, we don't have to stop there. I mean, that we could have done in the 60s with linear programming, right? But let's do something neat. We'll do LP fitting. I mean, if we can do a 1 norm and a 2 norm, why can't we do a P norm? Well, we can. So here, and notice how fast that was. So I fit a whole bunch of different norms, 1, 1.5, 2, 3, okay, all using the same conic optimization problem, okay? It's done the transformation to cones as Nina for all those problems in the instant I push the button. So that's how fast these solvers are, okay? And again, you can see the range from, here's the 1, 1.5, 2, and then you get to, eventually you get to the infinity or the max norm, and you get more sensitivity outliers there. So I think that's just sort of an interesting thing. So you can expand your horizons from just a few things to a whole bunch of things. Okay, now let's do a different kind of fitting, and this is called cardinality constraint fitting. So suppose I say I have these 4 basis functions, 1, x, x squared, x cubed. Suppose I say I want a fit that only uses 2 of those functions. Okay, and so the cardinality of the basis is the number of non-zero components I'm using out of the basis. This is another way of, and sometimes people call that the L0 norm. And Paratosh will be talking more detail about some of these methods. Let's change this back to 2. I changed this for so if I do n allowed. Okay, so there's a trick here. So again, I've used this inactive plus. I'm using quadratic optimization because this is a quadratic. I could use conic optimization and use that transformation to a linear objective. If I show it's just convenient with quadratic optimization. Okay, so here's a trick. So I'm going to set up, in addition to my coefficient vector c, I'm going to set up a w vector, which are integers. And these are going to be binary. They're going to be either 0 or 1. Since they're integers and it's constrained between 0 and 1, it has to be either 0 or 1. Okay? And then I let the number of non-zero ones be the total I'm allowing. And here's the trick. I find a bound that's as big as any possible coefficients I think I'm going to get. Okay? And then by bounding this is a trick to get a linear constraint instead of a nonlinear constraint out of that. And this is very common in mixed programming. Okay? So I do that and I get a weight vector. So this says if I'm going to do this, I'm going to use only the first and the third coefficients. And if those are the even coefficients, then that distribution of points I had was kind of like a quadratic. So an even function is going to obviously fit it best. Okay? And then we can show those fits versus that. And it's quite similar. So it's not much worse if I only use two basis elements. Well, now the reason I'm showing this problem is, well, first I think it's kind of neat, but it also shows a principle that's often used in convex optimization, which is the idea of relaxation. So you have a problem. Now that mixed integer problem is solvable. The solvers did it for small size. But if I started to do a big example, boom, you're going to be waiting a long time, even with efficiency, because the branch and bound stuff takes a long time. Okay? So the idea is, well, can we solve a problem that's nearby that will kind of get to the same solution? So can we relax the original problem, look at the solution, decide whether it's adequate or not, and go with that? And the answer in this case is yes, we can do a relaxed problem. So there's something called, and there's regularized fits, and that's been a common thing in statistics and stuff. So we're going to use the same norm, the same 2 norm, but here I'm going to add a parameter lambda times the 1 norm of just the coefficients. So the idea is I want to limit, so I want to balance between having the least squares fit be as close as possible, but I also want to keep the coefficients small. Okay, so what does that do? Okay, well let's look at the fit that actually gets me. Okay, so we can find it for say a particular value of lambda, and notice I'm just getting a fit vector now, so I'm not actually writing out times the whole basis. I can do that for plot. So it turns out that if this lambda gets big enough to keep this norm small, it's going to be zeroing, and this one is getting close to 0, right? So if I go a bit farther, it actually can zero out some of these coefficients. So what I'll do is, and this is using some sparse array tricks, but I'm going to threshold, because remember that optimization has a tolerance. So it might not be exactly 0, so I'll threshold under the tolerance to get zeros, and then I use sparse array and count the number of non-zero values in a sparse array too. And here I can do a plot as a function of lambda, the number of non-zeros that we get as a function of lambda. Okay, so here for the smaller lambdas like I showed you, you get 4. Eventually we get to that problem we solved before where we get 2 lambdas. Now the question is, and it can actually be proven, I'm not going to do it, but any of these solutions with the 2 basis functions use exactly the same basis functions as that cardinality constraint limit. So the relaxed problem, so basically with this relaxed problem, if I want 2, instead of solving the whole mixed integer problem, I say, okay, well I'll do this L1 regularization, get the number of zeros I want, boom, I'm done. Okay, so that's the idea. Okay, so now let's look at a big problem we can do with this sort of thing. And this is called basis pursuit. So suppose I have a huge basis of thousands of functions, often called the dictionary. Okay, and I want to find a relatively few number of basis functions so I can get a good approximate function out of that whole thing. Now here's an example with Gabor functions. Okay, and I'm not going to actually run this because I've pre-computed this. The Gabor functions sort of look like this, and these are 6 different examples of them. They shift, the centers shift along this axis, and then the frequency shifts as well. Okay, I'm going to set up a dictionary of a bunch of these, which so I'm going to subdivide the temporal space. I'll subdivide frequency, so on and so forth. So I get a whole bunch of basis. I make a design matrix using our design matrix, which is sort of a companion thing to fit. Okay, and oh dear, I think I might have erased the. examples here. And this is, well, actually I think this will work, so I'll try and actually run this. Okay, so this. Okay, now the key thing about the length of the basis is it's a 30,000 element basis. Okay, now any useful function model is not going to have 30,000 basis elements. Okay, that's not going to be useful if I do a least squares fit. I can get the design matrix for that. That's a pretty big matrix. It's a 500 by 30,000. So if I actually run least squares with this matrix, it's going to take a long time because that's a big matrix. Okay, it has to do an SVD on this matrix. I'm going to reduce the basis matrix size a bit by thresholding again, because those Gabor functions drop off quickly, so I'll zero those out to get a more sparse thing. Now let's consider a signal. Okay, so here's a signal. This comes from Boyd's book on convex optimization. Okay, we'll discretize that by discretizing over my time intervals. And now we can do an L1 fit. You notice that takes a little while. And here I'm using fit. So we've actually directly put regularization into fit. So you don't actually have to go through the convex optimization functions. You can just do it with fit. Okay, and that's documented. And notice this returns a sparse array. It tells me I found with lambda equals 1, I found 53 basis elements. So I've reduced that 30,000 to 53. Now, how good is that? Okay, well, there's one more thing you have to do with the regularization is that optimum I found is for the balance. And once I've chosen the basis elements, I actually want the L2 fit just using those basis elements. And so that's what these extra steps are for. So let's compare the signal and our approximation. Okay, and it's pretty good. In fact, on this plot, they're both plotted, and you can't tell the difference. This is actually the difference, and the error is fairly small. So instead of 30,000 elements, I've gone to 53, which I think is a significant. Okay, so I've got to keep moving. I'm going to skip this total variation regulation because I want to get to the next one, and I'm speaking too long because I want to get to this image, which I really like. Okay, so the idea here is we want to reconstruct a corrupted image. Okay, so here what I've done is I've taken an image, and I've so we have positions where the pixels are known to be correct, and other positions where the pixels are not known to be correct. And you want to sort of in-paint between the correct pixels to guess what the best ones are. Okay, so here's my corrupted image. Okay, the convex optimization, what I want to do is I want to minimize sort of the local variation from one pixel to the next. Okay, and I take the two norms of all those, the sum over this, so in the image size, it's a quadratic number of terms in this sum. And these each are modeled by these second order cones he was talking about. And then I require that it equals my data at the known positions. So that's it. I can actually do this with n minimized directly, but there's still some processing issues I'm working through, so it takes a bit longer. So what I'll do is I'll write out the norm constraints. Okay, those are the, so I'm going to convert this to a linear objective with that transformation I showed before. So I have a bunch of those. Here are my equality constraints. Maybe I didn't enter the, I didn't. Yeah, I don't want to run this anyway. Because that's the absolute timing. So this image, which is not huge, it takes 74 seconds to do, which is quite a few, but it's quite a few. It's 500 by 500 essentially. So you're talking about 25,000 pixels to work out. So the sum of 25,000 elements. So let's look at the actual results. Okay, that's my reconstructed image. Okay, which I think is appropriate for today's topic. And I just closed the wrong thing. Let me open this. This is the original image. And you can hardly tell the difference. Okay, so it's actually from that corrupted thing, you couldn't even read the big cone. Now you can read it again. So it's an image. Okay, so geometry, I'm going to, so I'm out of time. So I'm going to skip geometry, but Nina showed a couple examples there. So, and then the last one, which I'll just go through quickly, is, because it uses the dual, is the max cut problem. So the idea, and I'll go like a minute or so I'll be very schematic on this. The max cut problem is, how do you divide a graph so that the vertices that divide it have maximum weights? And it's an NP complete problem. Okay, so again, we're using this theme. To solve this, we're going to use convex optimization, but we're going to solve a relaxed problem instead. So we can actually write the problem out. And I'm not going to go through all the math, but it depends on the Laplacian matrix of the graph. And now, right, and then you can actually write an exact function that does it, and this can take forever for big problems. So we'll set up E sub I. So, and basically what we eventually get in terms of this is we get our problem. We want to maximize the trace of this. Well, if you look at the page for semi-definite optimization, this is exactly what the dual problem looks like. So instead of remodeling, what we'll say is, okay, we'll give semi-definite optimization these matrices, and we'll just get the dual solution out, and that will give me the solution for my max cut problem. It turns out you have to do a bit more. You have to process the matrix you get out, the semi-positive definite matrices, to see if it satisfies the conditions. But we can do that. And now we can actually test it on a real graph. So here's a Peterson graph. And we can find, oh dear me. Not quite sure why that didn't work, but it should show the actual. So it's not. Not quite sure why. Oh, did the space come in? Yeah, thanks. That so the. Right. So okay, thank you. I must have put that in. Yes, there it works. Okay. So, and that's solved almost instantly. Whereas the exact problem we'd still be waiting till past my questions. Okay, so quick summary. I've shown a few applications. There are many more. A lot of these applications I showed were taken from our reference pages for the various solvers, and we'll be adding more examples as we go. So that's a quick overview of convex applications.